Hey, welcome back. So, large language models such as GPT really struggle to reverse words. And today, I'm going to explain why. So, just to kind of prove this, I've gone on to po.com for a second and I'm going to ask it to reverse the following word. And the word I'm going to use is elephant. And when I put that in there, you can kind of see it makes a complete and utter hash of it. ELEPHENT. It just cannot get it right. The good news is if I go into GPT even 3.5 and say reverse the following word, and we'll put in elephant again, you're going to see that GPT 3.5 gets it completely right. ELEPHANT. So it doesn't struggle. So GPT used to struggle with this, but it's got a lot better. But GPT 3.5, by the way, isn't infallible. So if I say reverse the following word, and then I put dot append child, and I'm using this word for a specific reason, and I'll explain a little bit later, you're going to see that GPT 3.5 makes a complete hash of it also. And if you think that GPT-4 is any better, you can see here it makes a complete hash of it as well. It's missing the D on the append child. However, if I spell out the letters of the word individually by placing a space in between it, you can see GPT-4 has suddenly become competent and is able to now reverse the word. And that phenomena is not exclusive to GPT. If I then do the same here and just spell out the word elephant, you can suddenly see that Llama 2 that couldn't spell the word elephant before, it suddenly became a genius at spelling and is able to spell the word. So what's going on? Large language models don't see words like we see words. They see tokens. So what do I mean by a token? So if I take the word fish, for example, that actually is a single token. If I take the word fisher, that is two tokens, and the two tokens are fish and So when the large language model is being trained, it will actually be being trained on fish and not fisher. And therefore, it makes it really hard for the large language model to be able to do things like reversing words because it's not looking at things at a word level, it's looking at things at a token level. So today I'm going to deep dive with you the tokenization model of the GPT models, and that is a token library called TikToken. And then I'm going to show you exactly how some of these words are tokenized and detokenized, and then that will give you a really good understanding of what the GPT model is seeing. Now, in other models, such as the Mistral models or Llama models, they use a different tokenizer. However, the fundamentals are the exact same. But today I'm going to focus on TikToken, okay? So to get started, we need to install TikToken onto our local machine. So I'm just going to do pip install TikToken. And then as you can see, it's already installed on my machine, but that will get that installed onto your own machine. Next thing I am going to do is we're going to create a very simple Python file. We'll call it main.py. And then we'll start using that Python file to start encoding words. Again, this might seem a little technical for some folks not familiar with Python, but it's actually super easy to do. So now that I've done that, I am just going to open up that Python file in Visual Studio Code. And as you can see, it's completely empty. And we are just going to import the TikToken library. So the next thing I need is access to an encoding. So to do that, I'm going to type encoding equals TikToken.get_encoding. And I'm going to pass in the encoding as CL100K at base. Now, I could specify that I want GPT-3.5 or GPT-4 specific encoding model. The encoders are slightly different for each of the GPT models, but for the purpose of this video, I'm just going to stick with CL100K base. And now I want to do is pass in a string to be encoded. So in this case, I'm just going to print out encoding.encode, and then I'm going to pass in the string hello world with an exclamation point. And now that I've saved that, if I do python main.py, you're going to see it is 3 tokens. So you see 15339, 1917, and 0. And you can probably take a bit of a guess how that's been tokenized. So 15339 is hello, 1917 is is world, and 0 is 0. Yeah. And if I wanted to, I could kind of prove this. I could just take this here, and then rather than calling encoding.encode, I could do a print encoding.decode. And now if I pass in the array of the tokens and then hit save and then run this one more time, you can see that those tokens come back as hello world. What I want you to notice here is that the casing is maintained. Hello world is all lowercase. Now, if I wanted to split this up a little bit, I'm going to pass through 1533, 9, 1917, and 0 individually. And then we will just run this one more time. And you're going to see that it comes back with hello, space world, and exclamation point. 3 tokens. And again, that's probably quite interesting to everyone. In this particular case, hello is a token, but actually space world is a token. So rather than it just being world, it is space world. Now, that's quite interesting. So if I change that to from hello world to hello Chris, let's clear that again and then run that one more time. You see I've now got 1533952369091 and 0. And that is probably because the space is now coming in here. So actually, let's just put that in, and we will put in 5236091, and we'll stick with the 0 there. Let's just run this one more time. And you can see the tokenization, again, here is even more different than you would expect, right? The hello is maintained, but now I've got a space CH, I've got RIS there, and I've got exclamation point. So what's actually happening here is that within the vocabulary, there is common words that are being used within the data sources, and then they're being mixed and matched and combined. So when TikToken is looking to compose a word, it's looking at common elements or sub-elements to combine words together. So in this particular case, it's thinking, rather than using the word Chris, it's using space CH and RIS, and then it's combining, because those are things that are being used commonly in different spaces. So to come back to the hello world example, I'm hoping you're starting to see that this is really just a dictionary type operation. I have an integer, so 15339 is represented by the word hello, and 1917 is represented by the word world. And again, when training is happening or when inference is happening, essentially these sentences, these words are being converted into tokens, and then that's what's being passed through. And again, as I said, it's maintaining APIs. But of course, if I want to do different variations, if I was just saying hello world without the exclamation point, then I'd just be passing in the tokens 15339 and 1917 without the 0. It is basically a dictionary. Now, if I want to come back to the hello world example for a second, if I change this from hello world to hello world with capital H and W, and then even if I make this all caps for a second, you're going to see I'm going to get a completely different result. So if I just run this one more time, there's my original hello world, but you see hello with a capital H is completely different from hello lowercase. And then all caps hello is different as well, 51812. Now, world with a capital W is 1917, and then 4435 is completely different there, so world with a capital W. But look here, for everything all caps, something is completely different. And again, if I take those values, 518, 12, 16, 23, etc., and then if we run it through the decoder, as you see I'm passing through each one of these tokens individually, we can see exactly how it's going to be decoded. And as you see, hello world in capitals is translated into HEL low, and then you've got space world there and then an exclamation point. So it's an interesting vocabulary. And again, we can do the same with different words as well. So if I take the word fishmonger, for example, and then we run that through here, you can see that splits into 3 tokens. You see 1868, 7225, and 261, and you can probably imagine what this is going to be. It's probably fish, mong, and then and we can probably prove that. And then rather than doing a decode, I'll just paste that in, and then if we run it one more time, you can kind of see 1868 matches this token, 7225 matches this one, and 261 matches. So it's fish, mong, And then probably if I wanted to, if I could do some combinations, so I could take the word fisher, for example, and then what should probably happen is if we remember the decoding, that was 1868 and 261. So if I was to run that now, let's just clear this, we should see it is matching 1868 and 261 because it's the combination of fish and And again, if I want to run my decode on this, so if I take 1861 and 261 here, run that through as this, we'll just change this to a decode, we'll save that, and then we'll run this here, and now you can see it's taken these fish and and then it's combined that to make the word fisher. And that's how tokenization works. And as I said, I'm showing you the exact tokenization library that the GPT models use. So if I wanted to, I could actually just loop through the dictionary and print out each token. So here I'm starting from 0 and I'm going to 50, and then I'm literally doing a decode as we did before. Now if I run that in Python, you're going to see lo and behold, and it shouldn't be a surprise here, it is basically, there's our exclamation point that we saw earlier, 0, there's a quote, so you can sort of see it's just literally going through the alphabet in the beginning here. And again, if I go a little bit further, so rather than doing 0 to 50, if I do 1050, for example, and then you can see a whole lot of other tokens there. Indo, element, pect, ash, use, seption, nth, include. Now, anyone who's a little bit astute amongst us there, you can start to see that there's a lot of code is being run through this. So things like elements, etc. And it's even got words like const, ponce, maybe that relates to response. You're starting to get the idea. So it's not just restricted to things like the English language. It actually works with programming languages. So in order to have an efficient programming language, then some of the commonly used tokens are being passed in there as well in order to maximize the tokenization. So far, we've focused on English examples, but actually let's throw in some Japanese words. So I'm going to throw in Japanese for hello. I'm going to put the Japanese word for elephant, for fish. I'm going to put world in there. So that gives us 4 different encodings. And now if we run that, you can see the tokenization. So there we go. The Japanese for hello is actually got its own individual token. So it's used enough there to justify a token. The word for elephant is also got its own token as well. So, 47523. But if we look at the next ones, so if we look at fish and world, again, fish, even though it's a single token in the English language, in Japanese, it's being made up of 3 tokens. And then same for the word world, again, is being made up of 3 tokens here. And that's because the Japanese language and text hasn't been tokenized to the same level as the English language. In fact, it's probably not even been tokenized to the same level as programming languages. So it's maybe handling some of the common words such as hello, but outside of those really common words, and I would argue that they're probably common words that are appearing in English text, I'm really paying a penalty for the Japanese language, and that penalty is I'm using more tokens for the training and I'm using more tokens for the inference as well. And remember, you are charged on token usage. And this penalty that you're paying isn't restricted to things like Japanese. It's also restricted to other languages as well. So things like Swahili. So in Swahili, jambo means hello, dunia means world, and samaki is fish. So again, if I run this in my terminal, and we'll run this one more time, you see, although I'm passing through 3 words, hello has got 2 tokens, probably because it's using the English word jam and bow together. The same for the dunia. You can see dunia is actually 3 tokens, 67359 and 689. And then you can see fish samaki is 2 tokens, which is probably Sam and then Aki. So again, even tokenization is highly biased towards the English language and text, which again makes sense for things like models trained on Chinese text, or I think some folks in Norway are training languages on Norwegian text there. Then there opens up this space to have models that are natively trained on individual languages where there's enough text, and therefore you would see that would have an impact on tokenization. You would see tokenizers for those models more tuned towards that language, and therefore the cost of training, the cost of inference is going to be much lower. Where you can see the cost of inference, the cost of training for something like the Japanese text or for Swahili is going to be much higher, because you're using far more tokens than you would for something that's really focused towards English language. And you can kind of see the OpenAI model is highly tuned towards English language. And again, maybe in another video, we'll explore some of the other tokenizers. Now, if I wanted to get really crazy here, I think one of the things that we could do is get out of the realm of spoken languages like Japanese or Swahili or English, and we could move into something like a signaling language like Morse code. So if I look at Morse code here, that's how you say hello in Morse code. It's lots of dots there and dashes and things. Same with world there. And then we can just sort of print that out. And I'm printing out the final version just to remember everybody what it looks like. So if I save that, we'll clear our screen for a second. And you see for Morse code, if I was getting the large language model to work with Morse code as a language, I am paying a high tokenization cost. 1975, 662, 12, 497. So in the English language, hello would just be one word. It would be hello, it would be one token. Whereas in Morse code, hello would be made up of 1, 2, 3, 4, 5, 6, 7, 8, 9 tokens. And world would be made up of 1, 2, 3, 4, 6, 7, 8, 9 tokens as well. So in the case of Morse code, it really doesn't understand Morse code as a language. It's really just working with the dots and the dashes from a tokenization perspective. And now if we wanted to, we could actually just decode all of those tokens that we see over here just to see what it looks like. And in this case, I'm just going to decode hello, and then we'll run that one more time. You'll see there space dot dash dot. So again, it's handling the spaces really weirdly. It's just trying to group up things that's commonly seen, which is sequences of dots, etc. Again, there is no correlation to hello world. So when I'm dealing with something like Morse code, I'm going to be paying a very expensive tokenization price to be able to translate this. So I think this example really demonstrates that if I then got something like Morse code and I'm building a large language model that handles Morse code, it may make more sense to have a completely different vocabulary, a different tokenizer to handle Morse code as a language, one that is focused on the tokens of Morse code. So rather than having dash and having it translating into lots and lots and lots and lots of different tokens, then I may want to tokenize all of those dots and dashes, etc., just into a single hello world, etc. And therefore, I could have a vocabulary that's made up of sort of English Morse code as opposed to sort of paying the penalty of all of these split out tokens. And again, that's the same for anything else, whether it's Japanese, Chinese, Swahili, etc. Same sort of thing. So, and again, that's the same for programming languages. So if you've got a programming language that isn't one of the main flavors, maybe it's an esoteric language, for example, then you're going to be paying a high cost of tokenization because you're going to get into this same piece that the vocab of that programming language isn't in the dictionary of your tokenizer, so you're going to be paying a higher tokenization cost. And since I mentioned programming languages, why don't we, for fun, I'm going to do the encoding of a whole bunch of different symbols. So if you've got a bit of programming experience, you might recognize some of these. There's the not symbol, here's cons, here's enums, here's a little bit of TypeScript, colon string, colon number, colon int. Here's our arrow functions here. Here's a sort of Pascal style begin statement. If you're in a bit of VB script, you might recognize the word wend. Here's a bit of bash or algol with elif. Here's a .text box for JavaScript folks, and here's a .append child here, which again was at the beginning of our examples again for JavaScript and DOM stuff. So again, if I run all of this, the thing that is interesting in all of these cases is every single one of these is a single token. So if you think about this for a second, think of like Norwegian, Swahili, Morse code, all of that was being split up massively because it's not part of the vocab. But you can see the tokenizer for OpenAI, TikToken, is highly optimized towards programming language because you see all of these common operators that you have in JavaScript, Python, etc., is already built into the vocab, so that when we pass through a piece of JavaScript or a piece of C or a piece of Python, then it's minimizing the amount of tokens that we're sending and the amount of tokens that we're getting back as well. So obviously some of the older languages or esoteric languages, then what you're going to find is that those keywords may not be part of the tokenizer, and then it'll get split into different tokens, and then that will have a higher cost. So again, that's something to kind of be aware of. Maybe you're looking to train a model for your custom programming language or something. You can imagine that you may want to have a vocab that includes those keywords that you have there. But out of the box, TikToken, OpenAI's tokenizer has programming languages and common words used in development as part of the vocabulary. So therefore, when you're taking that text, your source code, and you're tokenizing it, these are getting translated into individual tokens. So it's not just optimized towards spoken languages, it's also optimized towards programming. So let's come back to what we said originally. Why can't LLMs reverse words? And it's because it's not dealing with words. They're dealing with tokens, and they're dealing with words that have been split up into different subtokens. So therefore, it gets confused. It's just like, I don't know what this word is. I don't know what to do with it is. And then it starts trying to basically provide gibberish on the way back there. However, as you can see with the tokenizer, if I can break the token, so rather than having a single word like the append child, and that's why I put append child in there, because it was a single token, even though it looks to us like a lot of letters. Then even GPT sort of struggled with that. However, if I get it to split it back into the individual characters, .a, space, p, p, e, n, d, etc., so it's dealing with things at an individual letter level, then it's able to do the split, and then it can reverse the word. Now, that's obviously, you've seen how that works for GPT. Now, obviously for other models such as Mistral or Llama 2, they use different tokenizers. So I think the Llama models use the centerpiece tokenizer, and then Mistral's got its own one as well. Again, you can use the same technique. You can take that individual model. Maybe I'll do a shorter video on that at some point, just to show you how to do that with their tokenizers. But again, you can then have a look and see what's in that tokenizer and see what it's doing underneath the hood there. But the same problem that you're going to have, and that's why the Mistral models, etc., the Llama models all have the same problems with trying to reverse a word. Now, GPT used to have problems with this. It's got a lot better at it, as you can kind of see. I suspect, I haven't seen the data underneath the hood, but I suspect what they're doing is they've got some sort of fine-tuned prompt that's saying, hey, when I ask you to reverse this word, I want you to sort of split it into individual letters like this, and then do the reverse and spit that out. I imagine the training is going to look at that. And that could be a fun and interesting video to see if we can train one of these existing models like Llama and get it to be able to reverse words properly. So maybe we'll handle that in the next one. Anyway, I hope that you've got a better understanding of how tokenizers work there. Maybe in a future video, I'll show you how to build a tokenizer for yourself, but hopefully this was a little bit useful, and I will catch you on the next video.